Again, the same thing that I'm going to tell you people, kindly don't think that it's a repetition. It's the same laser, it's the same nonlinear optics, concept remaining the same. There will be few overlaps, more of the same thing that you'll be listening, but this is going to make you more refined in the field of nonlinear optics. So to start with, before I go into anything, I'll just start with the basics. I'm not going to talk about the lasers, but I'm just going to tell you one thing that all of us know. We have got two types of lasers. That's a continuous wave and the pulse wave based on the mode of operation. So I'm not going to talk about what is continuous and what is pulse, but we people should be knowing that continuous means the output from the laser is going to be a continuous output of light. And in pulse, as you can see, the photons are not going to be continuously coming out, but depending upon what sort of a laser it is. Like for example, the nanosecond, pico, femto, atto, what type of laser it is, it's going to be the pulse laser depending upon the pulse shots that are going to come out of it. Why am I talking about these laser types? And remember one thing, the common mistake that these people we make is continuous lasers, we always talk in terms of wattage. It's deferred in terms of power, and the pulsed output is always in terms of energy, joules. Okay, so now even if you have a laser which is continuous laser, say suppose 50 milliwatt, 100 milliwatt, still it is harmless as far as you don't see it directly. But even the nanosecond lasers are highly energetic, and the 450 millijoule, 850 millijoules, even the slightest energy laser is going to create a hole in the cement wall that you have inside your lab, right? So these things you know, but why am I emphasizing on this? Because we are going to talk about the nonlinear effects. So what exactly is this nonlinear effect? We have seen in the morning, Dr. Reggie, Dr. Soma, and even our Sheikh Bahe had been talking about this, right? So depending upon what type of laser we are going to use, we are going to have the non-linearity getting changed. So the same question I'm going to pose you again, is it possible to change the color of monochromatic light? Mono refers to single, chrome refers to color. So you know it is going to be of single color and you're not going to filter out the other wavelengths. It's going to come out. But is it possible to change the color? Yes, since you have been listening to all the lectures in the morning and you have been in this field, all of you know that yes, it's possible. But there is always an if and but. So, but only when you have something like a laser light, right? So why laser? Why is that only my laser is going to help me? See, we are not going to look into the linear and non-linear optical part because you know non-linear optics basically helps us in controlling light using light. So photons in the sense can interact with your material and they help us in controlling another light. That's what I said. You can change the color of light, right? So why, how my laser is going to help me in getting this nonlinearity coming up. So all of us know that the atomic structure consists of a nucleus which is positively charged, having the protons and neutrons inside and the electrons going around. All of us know this, right? So since there's the electron and the positive nucleus, we have an electric field. And this electric field, because of this atomic arrangement, is around 10 to the power 10 volts per meter. But the conventional source of electromagnetic radiation, see, the magnetic field is very small when in the case of a conventional light. So the electric field strength is only of the order of 10 to the power 3 volts per centimeter. But we have seen that this is around 10 to the power 8 to 10 to the power 7 volts per centimeter. So they are not able to manipulate the atomic electric field. So if we have an intense laser radiation, this will create a strength of 10 to the power 8 or 9 volts per centimeter that will be able to exploit this, that will be able to go and involve itself within the electric field and change the properties. Okay, so this is so energetic that it results in the induced dipole moments, which can actually oscillate with higher amplitudes. Remember, smaller the amplitude, it can be able to show only, it will be able to show only your linear effect. But when the intensity is high, when the amplitude of the oscillation of your dipoles, we always say that the nonlinear effect dominates. When I talk about induced dipoles, obviously the next thing that comes to our mind is the polarization. So this is the equation that you will see anywhere and everywhere whenever we talk about the polarization, right? Nonlinear optics. So the first term, which is just, if you take just the first term, it is proportional to the electric field, which means that it is going to be linear part. Then E square, E cube and higher orders, as you can see, they are going to be the nonlinear part. And we are concerned more with the third order nonlinearity. All right, I just saw a few questions in the chat box in today's thing, whether we can go for higher orders. Yes, obviously. And Z-scan with just a slight modification in its, the way you align, you can have the fifth order also done. All right, so higher orders, we can go even with the Z-scan, you can find out. All right, now the same thing that I said, if it is going to be linear, the electric field and the polarization relationship is going to be linear, but it is not going to be linear in case of a non-linear media. So this is another important thing that we will be learning, that you would have heard about, the optical Kerr effect. Right. This Kerr effect, it simply says, you would have learned this in your PG also, the Pockels effect, the Kerr effect. This Kerr effect is what we are going to exploit here for our work. Right. So this Kerr effect means that whenever you have an intensity varying field, that can manipulate my refractive index. Right. The change in the refractive index will be proportional to the size. As you can see from the relationship, N, which is the nonlinear refractive index, is, sorry, the total refractive index is going to be N naught, which is the linear. But this N2 is along with the intensity. So my question to you people is it possible for me to vary the intensity? Can any one of you tell me, is it possible for me to vary the intensity? I think our chat box is open, right, sir? Chat box open again, sir.
Yes, ma'am. Yes, ma'am. The chat box is
So,
open.
anyone who knows the answer, I say it is intensity dependent refractive index. Am I changing the intensity here? Anyway, let me tell, I'm not able to go into the chat box. Still, let me tell you one thing. When I used to do my research, I used to get this doubt. When I'm sending a laser beam inside, am I changing its intensity? The same laser beam, say suppose 5 milliwatt, 50 milliwatt, whatsoever, when I'm able to see the intensity, okay, no. This is what my reply also used to be. No, intensity. I'm sending a 50 milliwatt laser, it remains 50 milliwatt. Where is the intensity changing? Right. Then how do you say that the nonlinearity is coming out because there is an intensity change? Right. So the answer for this lies in that the intensity of the laser is not changing, but the laser itself is actually an intensity dependent. Okay, the laser has a Gaussian profile in it, which actually helps in the intensity variation. Have you seen the Gaussian profile? This is what we call as the Gaussian profile. As you can see, it has got a peaking, right? The center of your laser, you just have the laser spot on the wall, and you'll see that the center of the spot is highly intense. And as you go towards the wings, its laser intensity goes on reducing. Towards the wings, one thing, it doesn't touch the axis, but it simply goes on reducing, having a peak at the center. This is the radial distance they are going out. So this is how the laser beam actually looks like. It's a peak at the center, so the intensity is highest at the center, and as you go towards the, it's actually reducing towards the wings. All right, this is what we actually call as the intensity variation. It's not that the power of the laser is changed or the intensity are varying by some other method, right? So the first and foremost condition, even if you're going to purchase a laser, the first thing that you have to ensure for this nonlinear work is that the laser beam should be Gaussian. Right. So the rest of the things are like, we have the phenomena that is involved in the second order. Is the most common one is the SHG. You have a crystal grown, allow the 1064 nanometers, which is invisible, and when it comes out, you see the green color. That is the harmonic has changed. The wavelength has halved. From 1064, it goes to 532 nanometers. It goes into the visible green light. This is what we have been saying, that yes, it's a nonlinear medium, nonlinear medium. But Sometimes we get disappointed when we see that no, there is no color change in the light. Invisible light is going inside. So no second harmonic generation means my material is not at all nonlinear. So discard the work. No, you don't have to be disheartened because third order nonlinearity doesn't require any structural requirements. All right. It's second order, which demands that it has to have a non-centrosymmetric structure. But third order nonlinearity, it can occur in any sort of material, whether it is centrosymmetric or non-centrosymmetric, structure doesn't matter. All right. And similarly, I just saw people who had put in the chat message whether, yeah, we can have nonlinearity in water, whether we can read it. Let me tell you, all materials are nonlinear. But only thing is the wavelength with which you are going to excite depends on. So that's why we say this work was done in a helium neon laser with 632 nanometers, but this was worked with the help of 532 nanometers large laser. So what says which laser to be used, that you can find out from the absorption curve. The UV visible light that we are going to take up, you see that it has got at least some absorption, even at the tail end if it is there, then only you can see the nonlinearity. All right. So depending on which type of laser you are going to use has to decide whether it is going to show the nonlinearity or not. All right. And all these things you have seen in the morning itself. So certain nonlinear terms that we have been using is the sum frequency generation or difference generation. But one thing is, we always say that we can have the frequency doubling happening or the wavelength getting halved. Like for example, 1064 nanometers, I can bring it to 532 nanometers. But is it ever possible for me by using my nonlinearity to have an frequency halving, wavelength doubling? Has anyone heard of it? 532 nanos. Can I make 1064 nanometers as a double? Is there any possibility? Have you ever heard of it? Have you heard of it? Anyway, find it out because there's a possibility. Okay, parametric oscillators. There are certain other things which if you learn, go inside deeper of our nonlinear optics, you will get to know about all these. All right, fine. So anyway, since you people have heard about all these in the morning, I'm not going to go back to these again. So periodic media. See, this is something that may help you while you are going to study about the application part. All right. So two-way mixing, phase conjugation. See, we can generate the phase conjugated beam, which actually helps us in the aberration correction. All right. If it's going to be a normal mirror, whatever is going to be reflected from it, the reflection can be seen this way. But if you are going to have a phase conjugate mirror, you can have the aberration correction. See, this is a light that is entering into the medium, which is going to distort my beam. This beam, when it hits the phase conjugator, reflects back. What you ultimately see at the end is going to be a corrected image. The aberration gets corrected because there is going to be a phase conjugation that is going to happen. All right. So that's the distortion correction property which we can utilize exploiting this nonlinearity. All right. Then we can have the four-wave mixing. Four-wave mixing is nothing, a simple one. You have beams which are in the opposite direction. All right. Now you're going to send a signal beam which is called as the read beam. When you see that there is another beam which is exactly going to be out of phase, 180 degrees out. It will be in the same parallel direction, and we call it as the phase conjugate beam. All right. So this input of two anti-parallel opposite side inputs you're going to give, you're going to send a weak probe signal, and finally you're going to see that you're going to get a fourth beam, which is the phase conjugate of this signal beam. All right, this is called as the phase conjugation. And as I told you, if you have the medium in which you can have the grating recorded, that is what is basically called as the hologram. Nowadays, you know what is a hologram, but the ones that is there stuck on the books or on some other thing, that's not the actual hologram by laser, right? If you want to have something recorded on a hologram, on a holographic plate, we have to induce some kind of grating like this, right? So you have one laser light, another laser beam, both of them interfere, giving rise to the grating inside it, which is basically the storing data. This is basically optical data storage. The data is now stored here. And for reading what is being stored, you again need one more laser beam. All right. So optical, this is what I was talking to you about, the optical parametric oscillations. Mm, mm, Let me not talk about this since we have less time. I'll straight away go into the optical switching part, which will help you in getting into your research. So if you look at the sum frequency generation, as I said, you can manipulate the light that is going to come out, right? For example, you have got a YAG laser, which has got one kind of a frequency. You have got a carbon dioxide laser. And if you have a nonlinear medium, a crystal, when you allow these two beams to go inside, you will get a third beam having a added up frequency. So this is the sum frequency generation. And similarly, you can have a difference frequency generation also, so that you have a change in your wavelength that is going to come outside. All right. So this. So let us go straight away into the third order nonlinearity, because we have something called a Z-scan. And here is what I'm going to tell you. We have got two types of lasers, the continuous and your pulse laser. Now, the continuous laser means the light is going to fall on my material continuously. If it is going to fall continuously on the material, there is going to be some sort of heat that is going to be generated within the material. So the localized heat that is generated is going to change the refractive index of the material, which is going to show as your nonlinear refractive index, right? But if you go for a pulse laser, like for example, a nanosecond, you know that the laser pulses are being shot as one after the other. It's not a continuous exposure. So what happens is whenever the beam hits, there is a dissipation of the heat. So the thermal effect is minimized. So as you people would have learned by this time, two types of nonlinearities can arise. One is your thermal nonlinearity, the other one is your electronic nonlinearity. Right. So by utilizing your continuous wave laser as an excitation source, the thing that we see is basically the thermal nonlinearity. All right. If it is a nanosecond laser, you can understand that the domination will be electronic nonlinearity, but there will be a little of your thermal nonlinearity as well inside. All right. But if you want to take up the perfect nonlinearity, electronic nonlinearity, femtosecond, pico or attosecond lasers can help, in which you can see the exact electronic nonlinearity. All right. So you people would have learned what is self-focusing and defocusing. And as this Z-scan, which is the topic of today, you can understand that the sample is moved back and forth the focal point of the lens. You have an aperture. If you have the aperture in front of the detector, it's the closed aperture. And if you have a lens to collect the entire light, replacing your aperture, that's the open aperture. So you would have seen all these, right? So this sample is moved back and forth the focal point. Since you see there's a lens kept over here instead of your aperture, this is basically your open aperture. This shows whether it's a reverse saturable absorption or saturable absorption. All right. So what we get from the closed aperture, as I said, you have an aperture in front of the detector. It is closed aperture, which is going to give me nonlinear refraction as well as a nonlinear absorption. But when I do the open aperture, remove this aperture and insert a lens so that the entire light is collected and sent to the detector. And this open aperture is going to help me in finding out the nonlinear absorption. It gives me the entire absorption. But now, when you need to calculate the refractive index, it needs pure refraction. No absorption part should be there. Close gives me both. Open gives me absorption. So how do I eliminate this absorption from this? I just take a ratio of these two. So in many of the papers that you people would have seen, directly from the closed aperture, the nonlinear refractive index is being calculated. Let us make a note that it is a wrong way of doing. We have to first eliminate this absorption so that you get pure nonlinear refraction. And how do I do that? We take the ratio of the closed to the open so that this is refracted and you get pure nonlinear refraction, and using this you find out the nonlinear refractive index. Using the open aperture, which doesn't have anything else except the absorption, you can calculate beta, which is the absorption coefficient. And this is the crude setup that we actually started our work with, having the sample kept. This is the laser, right? Aperture is this, and this is the power meter. We used to manually turn this, and then we used to change the position of this sample and the lens which is kept. So you can easily find out the reading onto the energy or the power meter and get the graph calculated. But now it's a crude way, because by the time you move, the heating may be there, the solvent evaporation may be there. So instead of it, now we have got something which is automated. Right, this is the laser source. It passes via this, comes here, the sample is kept. The sample is also motorized, which is controlled by this system. This is called as the C-scan controller. And using the filters and other things, you can have both your, this is the aperture. So this gives me the closed and this gives me the open. If you connect this to a system, you get the proper output of your transmittance directly onto the system. So this saves more of our energy and gives accurate values as well. Right, so this is the automated system. So close, see, negative and positive nonlinearity. So someone was asking what exactly decides whether it's a positive medium or a negative medium. It depends on the material, that's it. All right, but one thing is whether it is going to be saturable absorption or reverse saturable absorption, how do I decide? Let me tell you one thing, the same material which shows saturable absorption can change its property to reverse saturable absorption, or which was showing RSA can be showing the saturable absorption. You can get the details, even your organization, the survey has, he has proved that by changing the intensity, changing in intensity actually changes the behavior of the material, right? So this can be made to change the property by varying the intensity. So someone comes and says, my material is so good, mine has more nonlinearity compared to your material. They're comparing, but I am not sure whether we can go by that. The other experts who are here may give me some solution, because if I change the intensity, I obviously my values will change. I change the distance, my values change. I can improvise, or I can make show my material to be better than anyone else by changing the parameters. But as such, otherwise, we have got certain standardized setup for the materials that we are going to work on. But any other lab, if you're going to work with the same 50 milliwatt laser, but at a different distance, your results are going to be different. The sample that we are going to take, if you increase or decrease the concentration, then atoms which are going to take part in the nonlinearity is going to vary. So obviously the nonlinear parameters will obviously change. So I cannot compare a 2 millimolar solution of yours with a 1 millimolar solution of mine and say that yes, mine is great. Right. So it all depends. If you are comparing, just compare with those materials which are exactly being done under the same conditions like what others have done. Right. So the principle behind the Z-scan technique we have already seen in the morning. So this is what the output shows. So you have, when it is a far field, you have the transmittance which remains constant. There is a sudden defocusing at the focus and immediate defocusing. As you can see, that's the peak and the valley. So defocusing followed by an immediate, focusing followed by an immediate defocusing, and again the transmittance becoming the same. That means it remains the constant, right? And this is using a 532 nanometers. The same thing. This is for a positive material. Sorry. This is for a negative nonlinear medium in which the peak is followed by valley. This is a helium neon laser. And for the YAG laser, here we have got a valley, then a peak. So this is a positive nonlinear medium. All right. So open aperture, as I said, you can change. Materials have shown the property to change from RSA to SA or SA to RSA depending upon what sort of intensity I'm going to change. All right. So the formulae used, I don't want to go into. So the main thing that we have been talking about is about the limiters, the need for material which can help us in protecting the sensors. Why to go for sensors? Let's take the human eye, right? When the light is there that falls onto the eye, you see that yes, the eyes get damaged if you directly see. No need to directly see into the laser, damaging it. But otherwise also, if the intensity is more, obviously it damages. So what is our main aim? Even if there is an increase in the intensity of the input light, we need to restrict the output that is coming out. So this is the setup for optical limiting, in which you have got a variable beam splitter to change the intensity of this. And this falls on the, we find out the valley point from the Z-scan, and we keep at the valley point the sample and the same aperture. The same Z-scan, slight modification using a variable beam splitter, I can get the optical limiting done. And what exactly is the optical limiting? You're going to limit the output. Input keeps on varying, increasing. Output will also keep on increasing if it is linear. But if it is going to be a non-linear medium, beyond certain threshold value, whatever be the input increase, the output is going to be limited at certain output value. So that any sensitive instrument or your eyes or anything which is there on the other side of my laser is not going to get damaged because of the higher input falling on it. So this is the optical limiter, right? So next thing is the optical data storage, which is another application. And this, as I told you, is the holographic recording, in which you have got an object beam, a reference beam, both of them interfere, and the object which is there is basically recorded on the holographic film in the form of grating. Right. So this is the setup for the holographic recording, in which you have the helium neon laser, the red light coming, and here's the holographic plate. Right. So it falls on this, and you have got an NDR laser here, the diode pump laser here, which gives the green light. Right. So these two lasers interfere on this, and any object that is kept over here is basically recorded or stored in this holographic plate in the form of grating. So this is the formation of the grating, which you have as the central maxima, then the higher orders which are getting diminished. And once we have this recording onto some optical microscope observation, we see such gratings coming up, and this is actually having some information of some object which has been recorded onto this. You have another laser to read what is there, and you can make out what has been stored in this, and this is the holographic recording. All right. So our main thing that we are going to look into is the all optical switching. That is the now topic for us to have some sort of research that can happen, because limiting people have already started. Holography, it's almost done. So the next one that is going to be the next topic of research is this all optical switch. So this, what I'm going to talk about, will include why is it so significant, what's the basic principle involved in it, the classification method, the applications where I need to, and what exactly is the problem that we have to look into, and what is the direction which will help me in developing this. All right. So before we move on to that, let us see that there are 6 classes of all optical switches. Please, since you people may be at the early stages of your research, if you do not understand much of this topic, doesn't matter. Just have an idea what it is, and maybe you can employ this later during the course of your research. All right. So these are the 6 classes of optical switches, which includes optical coupler, Sagnac interferometer, Mach-Zehnder interferometer, ring resonator, fiber grating, and nanoscale. We will look into each of these. Okay. So this working principle of these are based on various nonlinear optical effects, which include the single photon or 2 photon induced nonlinear refractive index change or nonlinear absorption coefficient change. All right. Up to now, All optical switch research is in the stage of fundamental study, which cannot reach the technology indexes required by practical device, which has a low power, high speed, low loss properties. Okay, so in order to realize these technology indexes, what we need is we need to shrink the space scale of the devices. Then seek the high nonlinearity and low absorption materials, design reasonable and nano structure devices. Then we adopt the probe laser at the optical communication wavelength and a pump laser with ultra short pulse width. We have to use mature optoelectronic integrated techniques. Exploration of practical nanoscale all optical switches is present main research direction of all optical switches. So let us see why is it so significant. Okay, in the early 1960s, invention of laser marks that the optics started development from traditional optics to modern optics. Right. This so-called modern optics is the optics that uses laser as the optical source. And what is laser? It consists of coherent photons. So modern optics is nothing but just photonics. So nowadays photonics has already developed into optoelectronic stage, or we call it as a micrometer photonic state. And the characteristic of this stage is controlling light with electricity. That is optoelectronic hybrid. And devices used in this stage are being the semiconductor laser, optical modulator, amplifiers, detectors, and especially the electricity controlled optical switch. But if you see, all of them are controlling light with electricity devices. The application systems in the stage, such as the optical communication system, what we see in the computer system or the optical sensing system, are all optoelectricity hybrid systems. Right. So for the present optical communication system, what I mean to say is signal transmission may be all optical, but signal switching is still using the electronic technology. Right. So for the present computer, although the external input, output, all these equipment, storage, display equipment, they've all changed to photonic technology, but data process chips are still using the electronic technology. For the present, signal processing, which we may say as a demodulation technology, still uses the electronic method. So in today's optoelectronic stage, photonic technology has been widely used. Many electronic technology have been replaced with photonic technology, but the respect of core technology or the information processing technology, our photonics is far, far behind the electronics. So today's electronic information processing is digitalized because the electronics has a transistor and electricity controlling electricity device. However, up to now, we have no optical transistor. What do you mean by that? The light controlled by another light device. So it's the all optical switch. So today's optical information technology is only analog and not digital. Right. So the next stage of photonics will be a stage of all optical photonics, or we call it as the nanophotonics. So in this stage, the nanoscale photonic device will develop to light controlling with light, or all optical device. The digital optical information processing will be realized. The computer chip will adopt the all optical logic elements. Optical communication will use all optical switching technology. And all these optical technologies will be based on all optical switches. Therefore, now we say that all optical switch is a key technology of future photonic technology. All right. So what exactly is this optical, all optical switch? Right. So the development of electronics is based on the transistor. You know all, right? The fundamental device in the electronic computer is switching transistor, which is a device in which the strong electrical signal is controlled by a weak electrical signal. Now the laser has been invented for half a century. Why up to now people cannot make a practical optical switching transistor based on light controlling with light, namely the all optical switch? The primary cause is that electrical neutrality of my photon. Among photons, without strong electromagnetic interaction, there is no way to directly realize my light controlling the light. And the only way is using the indirect method. And what is that indirect method? Our nonlinear optics method. This is to drive the optical switch. That is, using a pump light changes the transmission medium of the signal light to realize the switching of my signal light. Now, in order to understand the working principle of the all optical switch, like in the morning, Dr. Soma Venugopal was also talking about this, right? We discussed a space type all optical switch based on this Mach-Zehnder nonlinear waveguide interferometer, like what is being shown here, right? Two arms of the Mach-Zehnder interferometer have the same length and different materials. One is a nonlinear material, maybe say suppose it is doped silica. All right, and another one is a linear material, say suppose it's the pure silica. Signal light with low power inputs the interferometer from port 1. This is my port 1. Divides it into two beams traveling in the two arms. Remember, because the Mach-Zehnder interferometer is symmetric, the signal light will output from port 2 and divides into two beams going to two arms, each having a power of P by 2. Hope this is understood. Right. Due to Kerr effect, the pump light induces refractive index change. Say, let me take it as delta n. And delta n in the nonlinear arm will be something like this, into the power by 2s, where s is the cross-sectional area of the waveguide. When the signal light passes through the nonlinear arm of the interferometer, there is a phase shift in the nonlinear arm, which is given by 2 pi by lambda delta n times the L, which is just the difference between the two phase shifts of the signal light beams in the two arms. We can actually prove that the intensities of the output signal at the two output ports are dependent on this phase difference delta phi. Now, when the power P that I'm giving here is strong enough to make my delta phi, the phase difference, to be equal to pi, then the signal light will be totally switched from port 2 to port 3. And when removing the pump light, the output signal will return back to port 2. Right. So this is called as the on and off of my switches. All right. So now, what exactly is the technology index? The practical all optical switches are required to achieve technology indexes, mainly in these three aspects. What are they? The switching power, the switching time, and the optical loss of the device. So what is the first one? The low switching power. This is needed. The switching power of around less than 10 milliwatts, like the signal power of the fiber communication. We need high switching speed. The switching time of less than 10 picoseconds, like the maximum switching speed of the electronic switches, and low optical loss, in which it is less than or equal to 0.5 decibels. But let me tell you, so far, it has been very difficult to achieve all these three technology indexes at the same time in the all optical switches. So what exactly is the problem that we can look into? So if you want to look into the problem, we should first understand that there are three contradictory problems. What are the contradictory problems? The first contradiction is between the switching power and the absorption loss. The all optical switch is usually based on the third order nonlinear optical effect, which requires high pump power. We have seen that. And the pump power is much higher than the control signal light power. So this high power makes a strong thermal effect, which leads my device to become unstable. In order to reduce the switching power, one needs to enhance the nonlinearity of the material. How can I enhance the nonlinearity? I can select the pump laser at wavelength of resonance absorption area. So that greatly increases the absorption loss of the material, which will make my optical switch fail in the cascading operations. Let me take the example. The semiconductor at wavelength of exciton absorption P has very strong optical nonlinearity, but its absorption loss is very high. Sorry, it's very high. Now, the quartz material has got low absorption loss, but its optical nonlinearity is very poor. And this requires the switching power to be much, much high. Right. Let us see onto the second contradiction, the contradiction between the switching power and the switching time, which we actually called as the switching speed. For example, let me take the optical switch using the liquid crystal material, which has got a high optical nonlinearity, but it has a low switching power. But its optical switching relays on the molecular rotation, and the switching time is so long. Now, an all optical switch using quartz material has high switching speed but low absorption loss, but molecule of quartz has high symmetry. So its optical nonlinearity is very low. So suppose I want to decrease the switching power of the quartz switching, one may adopt the ring resonator structure to increase the optical nonlinearity. Ring resonator structure, it's a very good option, but the photon lifetime of a ring cavity limits its switching speed. People can use 2 photon absorption to enhance refractive index change, then decrease the switching power. But 2 photon absorption, remember, it always accompanies the free carrier absorption that will again limit the switching time. So there is a contradiction between the switching power and the switching time. The third one is the contradiction between the switch on time and the switch off time. In general, the switch on time of all optical switch depends on the pulse width of the pump light. If the pump light used picosecond or femtosecond light, the switch on time can reach picoseconds. However, because of the limitation in the carrier recombination time or the molecular moving speed, the switch off time often is longer than the switch off time, maybe in the 2 orders of magnitude. Again, giving an example of a semiconductor all optical switch can achieve picosecond, but the carrier recombination time needs dozens of nanoseconds. So for this, one may adopt ultra-thin interface or non-uniform medium methods to enhance the speed of carrier recombination, but the contradiction comes because this non-uniformity in medium, though it enhances the speed of my carrier recombination, it may increase the optical absorption of the medium. So how am I to approach the problem? Saveri sir, how much time do I have? Saveri sir?
Ma'am?
How much time do I have?
Actually, you can go for another 5 minutes so that we can have 5 minutes for discussion at least.
All right, fine. So since I thought maybe that so many nonlinear works have come up, so the next approach for you people can be based on the optical switching. So there are actually 5 to 6 ways in which you can approach the problem. I can ask Dr. Sabari to maybe he can share this with you people so you can look into it, and there are 5 to 6 ways in which we can actually approach this problem and take it up as a challenge for our research work. So you can reduce the absorption loss, you can use silicon, silica, quartz materials, but one thing is the nonlinearity is very low. So you need switching power, as I told you now. So we can go for the micro ring structure, right? So this is one research area which you can look into. All right, the next one is the Kerr effect, which is going to help. So to enhance the photorefractive, we can use the 2 photon effect. Right. So the next one is like we have other physical mechanisms also that can help us in realizing this all optical switching. Right. So just one thing to remember is under the nanoscale condition, these new mechanisms are possible to obtain the low switching power and fast switching speed of all optical switches. All right, so let me just conclude this because since there's been different kinds of all optical switches based different working principles have different characteristics, functions, and application in different occasions. All right, so on the foundation of developing nanophotonics and ultraphotonics to compress the device space dimension and the pulse width of my driving laser, I need to adopt various nanostructures, new physical mechanisms, and at the same time to enhance the nonlinearity, the response time, and transparency of the material. Finally, the practical all optical switches are possible to be realized. All right. So maybe I'll conclude with this. So if you have anything that you people would like to discuss, I'm here.